Hello, everyone. Welcome to Memgraph's community call. So a little bit outside of the normal, regular kind of broadcasting hours. We're a little bit early today, and that's because we've got our speaker Art, who is based in Singapore. So
Hi guys.
today's session is super technical, primarily technical. We haven't done, I think, maybe as technical of a session in the last while as this one will be, and it's all about Kubernetes, which is obviously a number of people's favorite thing to talk about. So. Especially if you manage Kubernetes clusters, you will basically know the pain of managing them, of figuring out what's actually happening, how you kind of chain them together, how you connect the pods to services, and various other things. So basically, Art has built a graph engine for Kubernetes for agents, how to kind of manage that, how to do that easier. And he's built that through Memgraph, or on top of kind of using Memgraph. So basically, without further ado, I'll hand it to Art to walk us through. If you have any questions, kind of as we go through, feel free to pop them in the question chat in the question chat in the chat next door on the right, and then we'll probably get to them all at the end of the presentation. Art, take it over.
All right. Hi folks. I'm Art. Hopefully you can see my screen. So yeah. All right. So yeah, building a Kubernetes graph engine for agents. And I'm Art. I'm senior lead software engineer. I work at Agoda. Like many of our workloads are running at Kubernetes. We actually run on-prem. It's not cloud. And I got tired of asking the same question again and again, which is a connectivity question. For example, what would happen if I take out this node? Which public hosts will be affected by that? Or hey, what are the PVCs that are connected to a specific set of pods? You can definitely do all of this with kubectl, but kubectl helps you only to work with a single object at a time. So I built this tool. Let's go through it. So the problem, you have a large cluster or not that large cluster, and you keep asking the same question again and again. And it's you can do it definitely with Bash, with kubectl, with some Python scripting, but it all felt like a wrong approach. Again, kubectl is really good for like inspection of a single object, but when you start thinking in terms of connectivity, then you need to basically chain 5, 6 commands together and then join stuff and make sure that you did not miss any resource type, and then to come up with some of the answers that you're looking for. So I wanted things that kind of really helpful. They're not just for like one time, right? So there are 4 requirements that I needed. I needed a live model on the cluster. And I wanted my questions to be natural to the Kubernetes. So then I can ask questions like, hey, which containers are running in this namespace, and give me the images that they're running. So also, I didn't want to build 2 interfaces. I wanted to build one system that both humans, engineers, and AI agents can use. And also, I didn't want to take shortcuts because Kubernetes objects are quite big. I didn't want to start flattening it out to try to kind of fit it into specific type of databases. So yeah, like Ariadne just does a simple thing. Takes the state of Kubernetes cluster and it converts it to entities and edges and inserts it into as a property graph. That graph is stored as a memgraph. So then engineers can query it using Cypher, but agents or people also can safely walk through MCP. So the flow is simple. So the data flows from Kubernetes API to the Rust systems that I build that does snapshotting and has a diff engine, which makes sure that I don't pull the whole state of the Kubernetes again and again, but rather I do it smartly. That data is fed into Memgraph, and Memgraph is an execution engine of the queries. MCP server is a boundary between that Memgraph and humans. The things that I didn't want to expose the graph database directly to the AI agents because it's not that great idea. You need to do a lot of guardrailings. You need to understand which queries are allowed, and it's too dangerous. So I want to have a layer that I have full control over it, and that became MCP servers that I built. So you can say, I mean, but why graph, right? But if you think through, the Kubernetes is actually a graph because, for example, replica set manages pods. Pod runs containers. Nodes host pods. Like graph queries make this traversal direct instead of procedural, because you can, again, as always, you can kind of achieve similar things using kubectl and running multiple of kubectls and joining the results, but that's a procedural thing, right? But you can just have a query in Cypher language that explains all these hops. Let's look to a real Kubernetes graph, right? So this is a real cluster, and you can see there are already patterns here, right? Like there are pods that are staying close to deployments or stateful sets. They all are part of the cluster. So this is just a real cluster, a Kubernetes cluster that is rendered like a graph to give you more like visual representation of what we are talking here. Why Memgraph? The main reason for me, because Kubernetes objects are deeply nested, they're irregular, you can have maps inside maps, lists inside lists. And again, I didn't want to spend time on denormalization, and Memgraph was like super easy. You take this object, you fire insert, you provide the argument, that super nested graph object, and it just works. Also, I didn't want to take shortcuts. I didn't want to start denormalizing, truncating objects. I mean, I still do small truncation for security purposes because, for example, the config maps, I don't read the data inside it, just to make sure that it never kind of affect any security stuff. So yeah, Memgraph is super flexible, and I didn't need to do any normalization. And once you, another cool thing that I didn't, so it was not required to do any denormalization, is that LLM models have learned through the training or post-training that, hey, they're Kubernetes objects, they have these names, they have these fields. And I wanted to reuse this knowledge that LLM already acquired. So which means if I start naming things differently, it might confuse the model. So also another thing that Memgraph has native bold protocol with RSMG client for Rust. So it's a direct low overhead communication with Memgraph. I actually contributed to one small PR there. Because it's unsafe library, so there was a memory leak. I had to fix it, but the pull request was reviewed quickly and the fix got merged. So this is an example. You actually can play with Memgraph. It is provided as a Docker, so you can just create your Docker compose with two components, Memgraph and Memlab and Memgraph. And here is how UI looks like, and the query that tries to answer is the following. It tries to resolve the whole chain of Kubernetes entities that map a specific host name, or here set of host names, to the pods that are taking care of that. So to me, it's like really nice way. Of course, you need to know all these edges from different type of objects, but it's a nice way of presenting the connectivity between different objects in Kubernetes. And also, this is a good example of multi-hop multi-hop traversal. With kubectl, it will require at least 5-6 commands to get a similar level of information from there. So, okay, so Memgraph was a storage, but again, I don't just take objects from Kubernetes and dump them into Memgraph. That would be too dumb. So for that, in order for me to have a rich representation of the objects that we are modeling, besides actual Kubernetes resource types, I also model so-called logical nodes, things like container, endpoint, host, ingress service backend, etc. So this, plus on top, I have more specific edge types that I can use. For example, pod runs on a host, or a pod claims volume, etc. So this helps the graph to be queryable at the level that basically we care about. Because if you just, without introducing these logical node types, it would be, again, you just replicate the state of Kubernetes in Memgraph, but then you don't have these nice edges between containers and pods and hosts, etc. that kind of helps you to quickly traverse the graph. Architecture. So it's written in Rust, and the reason to go with Rust is that the ingestion and seek, I wanted to have a predictable latency, and also memory safety. So there's a core component that basically makes sure that everything related to Kubernetes, snapshot, define, and graph updates is there. I needed to have a way to validate the incoming queries, and for that there's a Ariadne Cypher crate that basically uses tree-sitter as a open Cypher parser, and then MCP, which is just an interface that basically combines everything together and provides a way, is provided as an interface that agents or any MCP client can connect. There are small things like tools that I use for schema and prompt generation. It's for some experiments that I was doing in Python for agent workflows. This is how things are connected. It's a simplified diagram. So you can see that the coding agent is an external thing, can talk to MCP server, and MCP server basically has, actually it has two modes of working with. One is you just point to the folder where it gets the data that it's already snapshotted. At the same time, like the production use case is like it just points to the memgraph and it goes and reads data from that memgraph. So yeah, there's a Python code here that I use for evaluation or for trying to find better prompt and other things. But yeah, main component here is MCP, that is an interface between coding agent or any MCP client and memgraph. A bit about why did I need snapshotting and incremental sync instead of just reading the whole state of the cluster. And the reason I wanted to have I want to be able to see the changes in the cluster almost immediately. That's the first reason. The second reason, it's super inefficient if you go and query all the Kubernetes objects again and again every 2 or 5 seconds. Currently, like I query them every 2 seconds, but it's done in a smart way. So during the bootstrapping, you go get the full snapshot state, which is expensive. It takes, it depends on the cluster side. It can take like up to 5 seconds, right? It needs to pull the state, derive things, and materialize it to the memgraph. But at the same time, once you created the initial state, then you don't need to do that expensive operation anymore. And on top of that, I'm using the so-called watch protocol of receiving changes from Kubernetes, when instead of the Kubernetes cluster the Kubernetes client does not always pull all the objects, but it rather receives a notification that these objects have changed, and it only pulls that amount, which makes sense because usually there are not that many changes in Kubernetes cluster always. So yeah, we full snapshot once we initialize, but we do incremental diffs for steady state. There are also flags to kind of reset the state from time to time if for some reason it got diverted. Maybe you lost connectivity with Kubernetes API and like you missed some of the diffs. But the idea is just that diffing is much cheaper than full resync, and also it does not require so many operations on Memgraph side as well. So these are some numbers from the real cluster. Again, it has around 3K graph nodes and 7.5K edges across 70 edge types. So the initial graph build takes almost 6 seconds. And once it is done, so in the steady state, it takes like typical diff takes something like 30 milliseconds. And to be able to understand how much is the lag between the current time and the last sync state, there are a couple of metrics that I track, and like typical freshness lag is around 1 and 1 second. So of course this will heavily depend on your cluster and the size of the cluster, but the thing is like you can use it for near real-time stuff. So yeah, kind of reiterate, incremental changes important. You don't need to rebuild always. Cluster changes constantly, but it doesn't change dramatically. So the sync cycles are very short. So this actually makes the MCP server that takes care of handling and syncing it basically reduces a lot of backend work, and it reduces both memory and CPU pressure. So the MCP is the agent boundary. So that's I actually spent a lot of time of doing things differently, but I landed in this approach, and I can try to explain why. So actually, if you want to play with LLMs that can use Cypher to query graph database, the Memgraph already provides this interface. The UI allows you to basically provide your LLM endpoint and the authentication token, and then you can basically, it provides you a way to, without building all of this, to basically try out your ideas. And this is what I actually did. I used that system to at least try to understand whether the approach I'm going to take is making sense. But going back to MCP, so why MCP? Originally, I decided to build Python engine using Google IDK, but then I understood that like it's too complicated. There's so many different moving pieces. Like, hey, how many sessions do I need to store? So it's not simple. Then I decided maybe to build small UI application, or that helps you kind of interactively work with Kubernetes cluster using human language that is basically transformed to Cypher query. But after like all of these experiments, I understood that like, there are already tools that are really good at reasoning. They are calling coding agents. So if I provide MCP as the agent boundary, not raw DB access, that will be a really good explicit interface. And I just needed basically 3 tools. The first is graph query. So LLM or coding agents will come up with a query and use this MCP tool to execute that query. Schema. So LLM, in order to understand what we are talking about here, it has to fetch the schema of the graph, the edges, the nodes, and the properties they have. So this is super useful because LLM will not be trying to guess, but rather with a schema, hopefully it will reduce the amount of hallucination. And also, I want to make sure that when this system is lagging behind for some reason, so the agent is aware of that. There's a graph health endpoint MCP tool that actually provides all these flags: the readiness, the freshness flag, which resources have been degraded, etc. So basically, once I actually understood what I need to be focused on, that MCP part, basically it made everything much easier. Uh, but easier, but it doesn't mean that it is still simple, right? Because uh, so again, I needed a schema. Schema should not be too long, but it should not be too short. Uh, I need model to know that, hey, we're lagging. What's the state of the MCP server, so we can actually trust the result. Also, like I can't let the model to basically query like thousands of rows of the result from the Cypher query, because I mean we are all limited by the number of tokens, so we need to be basically it has to have a bounded response size. So two things that actually made a huge difference is the validation of the query and structured error classification. Because once you can provide this information to the LLM, to the coding agent as a feedback, they're really good on reading that feedback and self-correcting. So that's why basically just instead of saying, hey, coding agent, this is a library, this is an endpoint, this is the authentication to this memgraph, go and talk to it. That's why MCP is much, much better in this. Yeah, like, important things that the MCP server classifies the errors to be repairable and retriable so that LLM can actually understand whether it has to try to fix a query or like the query is like completely unusable. All right, let me try to do demo. Let me zoom out here, stop sharing, and start presenting here. Okay, hopefully, folks, you can see my console. So this is how I'm running my MCP server. Hopefully it runs. Let's wait a couple of seconds. Okay, yeah. So yeah, it got connected. Yeah, so it is creating Memgraph now. Yeah, so it basically inserted everything in 4.5 seconds. Cool. Okay, so here I'm going to launch Codex, coding agent. So, and I created a specific layout of the folder where it knows about Ariadne. It knows it as a skill. So let me launch it. Cool. Let me ask a simple question. What is the status of me? So let's see whether things are working. Yeah, so it will go the first time. It takes a bit of time. It has to actually discover skills and then call the graph health, and it will give me the state of the cluster. Still thinking. Okay, cool. It is healthy right now. So yeah, there's not that much lag. So it sees the time, etc., the sizes, and yeah, all good. Now let's start asking quite complicated questions, I would say. So I'll just copy paste the question, right? Which deployment serves the specific host name? How many pods back it, and on which nodes? Okay, I'm running GPT 5.4 in X high, so it takes a bit of time for the model to think and run and stuff. Let's wait a bit. Yeah, you can see that it actually goes and asks for schema first to be structured. Yeah, it says, hey, I have a graph shape now. Next I will be resolving the host to ingress backend and the following through endpoint slides at actual pods. Okay, so it is thinking. It is thinking, it is making some MCP calls and continues thinking. All right, so yeah, here is it. Yeah, so again, 2025, quite close to current time. This is served by this ingress, which targets this service and maps to this deployment. And there are two pods that are back in this server, which is actually true. Okay, let's ask maybe an interesting question. For example, if I drain this host, which public host names are impacted? By public host names, it means that now you have an ingress that defines the DNS name that is handling that ingress. So yeah, let's see whether it is able to manage this query. Yeah, still thinking. Mhm. So yeah, it basically analyzed whatever it thought is reasonable, and it decided that, okay, if we put down this host, there is this endpoint that is kind of related to this host, and it is through this pod for this service, right? File config API. So the expected application impact is capacity reduction, not a full outage. Or not find any other public hostname currently. One caveat: the node also runs Envoy, which is a service mesh. Yeah, and one thing, this system is not aware of any extension to Kubernetes like service mesh, contour, Istio, etc. Cool. Okay, and one more question, maybe then. Let me ask. I think we still have some time. It's now about the persistent volumes and storage classes. So we need to understand again, like we have some service that is back in some pods. Do they use persistent volume? And what is a storage class? Uh, I mean, definitely I have chosen the questions that require multiple hops. So of course, there are other questions that could be actually answered by a single kubectl command, but that wouldn't be fun, I guess. Yeah, again, it wants to be quite precise. Yeah, it always tells what was the date, because this information, like, you don't want it to get it like after like having like some like 6 hours of stale data, right? So yeah, there's 4 services backend pods, and they have LVM as a storage class. Okay, I guess that's it for the demo. Let me stop sharing that and go back to sharing the presentation. Uh, cool. So that was a demo. Let's move on. So I started this project like quite long ago, and when I just started that, LLMs were not great at generating a good quality cipher uh, valid query from the natural language. And from the time I want to look to multiple dimensions, one of them was like, hey, which models is the cheapest one to run? Instead of course, of course, the frontier models are really good, but can we achieve the same running much cheaper model? And for that, I needed to I built some evals to measure the query correctness and what are the failure modes. Also, I tried to experiment with intermediate representation. The idea was like, oh, you know what, if LLM is not that smart, directly converting English to Cypher, let me maybe use LLM to create some intermediate representation as a JSON that then I can build a compiler to convert that JSON representation to a Cypher. The idea was interesting. I actually spent some time. I implemented spec. I implemented the small smoke test. It was all super promising, but when I ran the whole idea on the very big data set of my golden standard, so it wasn't great. So yeah. Anyways, the model quality actually matters, but I think what is more important is all the interfaces and validation in place, because you don't want to keep trying changing models without having actually any meaningful metric you want to track for. Yeah. I also try to experiment with DSPI. This is a Python library that helps you to improve prompts. It also didn't give me any, I mean, it helped a bit with like these Gemini Flash models or like Daimler models, but for frontier models, I mean, they're really good already. I didn't see any improvement. Yeah, again, typed intermediate interface, intermediate representation was interesting idea, not default. It was fun experiment actually, but yeah, um, the state of art models, the latest models are really good at understanding Cypher, uh, and instead of coming up with its own grammar for this specific intermediate representation, and also because uh, and I mean obviously the models during the training so much Cypher that they understood it much better than me doing one shot or two shots prompting saying, oh, this is my intermediate representation, and expecting that the model will follow it thoroughly. Yeah, but again, it wasn't that simple. And I needed to build all of these toolings, ISD parser, validation, because LLMs are stochastic machines. I mean, they hallucinate. They come up with a property path that do not exist, even though I explicitly my prompt starts with explicit schema, like all the edges of the graph, all the properties of the graph, all the entities of the graph with all the properties. But once in a while, LLM will decide that, hey, I mean, it will try to use the edge that does not exist. Or it will swap the direction of the edge, which is a bad idea because we are modeling the graph as like Kubernetes as a directed graph. So the direction of the edge is important. Uh, yeah. So it's like, yeah, from one side you want model to have a freedom, but from another side you want it to work within some constraint. Otherwise, like the system might not do what you really want. Yeah. So we needed better schema and better tool boundaries. So we always strive for perfection, but seems like with LLMs, I mean, you need to always expect that, yeah, it's not 100% correct thing. The question is how we can reduce the probability of it coming up with a wrong query. Okay, so with coming up with wrong query, I mean, I can't do much because I don't have an oracle that knows how the good query should look like. I mean, of course, I have like data set that I use for evals, but in real life, there are a couple of things that I can actually do, right? When LLM comes up with a Cypher query, I parse it to validate that it's actually a correct Cypher query. Yeah. So another thing I do, like the semantics, it has to be only read-only type of queries. It cannot use any call statements. It cannot update or insert, anything like that. Of course, it's not super thoroughly thought. For example, if like someone, I don't know, tries to encode base 64, and because I'm not a graph database engine, right? I'm just like a quite simple IST parser that here is used for that. So the cool thing of Memgraph is that it's schemaless. So which means that you don't need to spend time defining all the properties, all the edges, how they connected, blah, blah, blah. So you can just start basically creating your graph and populating your data. But because LLMs can hallucinate, they can come up with the edges that do not exist. And this is a valid Cypher query. You run it and it returns you nothing. And this is a problem because is it nothing that there was actually nothing and this edge exists, or it's nothing because the edge does not exist? And for that, again, during when I have IST tree of the Cypher, I actually validate all the entities that it tries to traverse and the direction. And this happens before sending the query to Memgraph, which which basically allows me to provide a proper feedback to the LLM telling, hey, this edge does not exist, or things like that. But of course, of course, this is all validation. The actual Memgraph is much more complicated. It supports like OpenCypher, like it's super complicated language, writing a really good parser that covers everything. It's so complicated. So I offload it to the Memgraph because it is what it is designed for. So yeah, Memgraph is source of Cypher syntax. I'm in Ariadne, it's just source of the graph semantics and safety for this specific use case. And the goal is just to make the safe pass the default one. And again, on every stage of this process, MCP tool returns error, a classified error that is providing extra information to LLM to try to basically self-correct on the next loop instead of just guessing what went wrong. Yeah. And again, as mentioned, like I can't let LLM to query like I don't know 10,000 rows of the response from the graph. So it has. I'm enforcing limits, and if the model decides to query much more, that's it's rejected. So it has to come up with other ways of getting more data, maybe chunking. One important rule that I have added, you might ask why, but basically, so I do not allow any filtering that is done in the match case. And the reason is because it does not work as many of us would think. And because the reason being that Kubernetes objects are super nested. And if you use the risky example of the match, you actually will not find anything because it does not match on that specific field, but it actually does the whole map equality check, which means that all these filterings will actually fail. And it's so funny because even in my prompts, I would explicitly say, hey, you should not use this. This is illegal. Use this legal. And once in a while, LLM will just ignore that rule in the prompt and decide to write a wrong type of match. So yeah, I was kind of tired of it, and I decided, okay, let me actually call this problem during the IST parsing validation and give a proper feedback to LLM saying, hey, you know what, you're actually not allowed to use this, please replace it by this. Of course, I can even go further and rewrite maybe on the MCP level these kind of matches. But again, this is already kind of like the age where like graph database engine, like it's not a simple IST parsing rule because it can be nested matches, etc. So I decided, okay, better just to reject and let that as a feedback to the model. A couple of words about the evaluation. So again, like how well the models can understand English and Kubernetes and schema of the cluster and can generate the correct Cypher query. Of course, this is super complex thing, but what I decided, I came up with 3 classes of the questions, easy, medium, and hard. And I use Python to write the eval a small eval kind of framework for this specific use case, which tracked not only validity, but also what are the errors and how many retries and whether retries helped. So the goal was like, hey, if I change the model, how well they're behaving? Or if I change the prompt, do I get better or no? And the results are quite actually interesting. So the frontier models like are really strong. So so basically you can see, but even GPT 5.4, it it does not produce 100% correct queries that return what I expected, right? So query validity is like that there's execution, it so basically there is a correctness and there is a validity. The correctness means that, hey, actually model came up with a query that I expected it to be, and after executing the query, the result is what I wanted. Or it looks like what I wanted, because it might decide to project differently the field names, but that's not important. Like this is all counted in the eval. But what was interesting that even like the frontier models sometimes did not understand, sometimes produced not correct queries. So, I mean, it might be a bit debatable, but you know, in the end of the day, this is my golden data set. This is what I expect to see, but this is how they work. Even it's interesting, like for example, the second top model, Claude Sonnet, the retry mechanism actually helped it a lot. So it did retry 3.7% of the times, which again, like models are great, but proper validation and interface design, I think, mattered more than the model choice. I also play with local models. Recently started playing with that, and I wanted to see how well is Gemma 4. It's a recent model released by Google is doing. And actually, I mean, they're not that great, but at the same time, they're not that bad, right? Like 85.8% of correctness for 31 billion model parameters. I think it's quite good. So yeah, maybe in some constrained environments, one can use them. Uh, cool. So far, so what was the journey and what I learned from it? I think the cool thing was Memgraph. It was like it just worked. Yeah, I was thinking how to sync the data, how to model extra things, but like working with Memgraph was less easy peasy. Just follow the spec and that's it. Incremental sync was important because without that, it's actually like full rebuild. It's not a scalable solution. Also, like the infra folks will come after me because full resync on the large Kubernetes cluster actually creates a lot of load on the Kube API. MCP is a right agent boundary, I think. And I was going back and forth, as I told, I was going Python and then maybe my own UI, maybe. And I was like, okay, you know what? Like coding engines are great. Let me just build that MCP boundary. Again, like changing models is also quite straightforward, right? Like you have it depends what library you use, or what coding agents you use, but it's a one-liner. But what was the difficult part was like the data shape. How do I do validation? And the most difficult one, how do I do evaluation? Because evaluation is a bit like more art than the science, because like you're asking a language in the human language, which is natural language, and there can be many different ways to answer it. Which one is correct? I mean, it's not obvious. Okay, what can Ariadne do next? For example, one of the things you can do, it can try to model more objects that are part of Kubernetes, for example, like service mesh, Istio, maybe AWS or GCP related objects. Another thing, because everyone now becomes very like conscious about the number of tokens they're using. For example, maybe I should try to add the progressive disclosure of the schema, because currently if the model asks for the graph schema, it can be like the full or small, but if it asks for the full, I just dump the whole huge schema of the graph. Maybe again, one of the ways would be like, okay, let me try to progressively show to the model what are the properties of different objects to save tokens. again, thinking about how to make the loop when agent try to repair itself more resilient, to better understand Cypher, again, maybe to rewrite queries with filtering that was not done right way to do it in right way, for example. Yeah, another thing could be useful is actually start really plugging this to the maybe SRE related work when basically anyone can use this to understand what's the impact of, like, I don't know, what is the potential impact of this system going down? Because currently Ariadne works only within single Kubernetes cluster, but in many places you will have multiple of the clusters. And then how would you model that, right? Of course, I build with the concept of the namespace and the cluster, but it would be interesting to see, like, if you have a bunch of clusters, how do they connect, where the connectivity starts, if something breaks, what is the kind of the place that you should be, single point of failure, etc. All right, I think with this we have come to end. Thank you. And here's a repository to the project. So please, feel free to check it out.
Cool. Thank you, Art, for the presentation and the demo. The demo is always a little bit of an anxious one, whether it's going to work or not. But we pulled it through, which was really good to see. For everyone else, any questions? There was two questions on the side. I think you answered them. The first one was about a different use case for this, the optimization from kubes CLT 5 commands to a single NLP command is big. Is there anything else that you have thought about?
Yeah. Sorry, Marco. I'm writing. Okay, there's answer.
Oh, it's a
No,
Q&A with the question mark on the side.
yes, I see. I'm writing something similar to your solution for S3. Are we talking about this or like?
So it's both. I actually don't think we covered both. So either question is
Okay, let me start because
okay.
I don't know the order. But yeah, I'm writing something similar to your solution for S3 without the MCP part, but I'm stuck on data drift. How do you efficiently detect that a certain resource is no longer in your Kubernetes cluster and propagate the information or display to the end user agent? The only way I see to do this by parsing the whole graph, but that seems expensive. Okay, that's a very interesting idea. What I'm doing currently is so. Yeah, it's kind of related to that snapshotting and diffing. So my Kubernetes clusters are large, but they're still, I can fit them in my memory. Of course, I can offload on the disk if I need it, but long story short, so when I read all the objects from Kubernetes and then I basically, I, I add extra objects that are not Kubernetes objects per se. For example, a container is my logical object. It has nothing to do with Kubernetes. So long story short, I assign a specific identifier to all these objects that I have. And that specific identifier contains things like, the object ID, the namespace, and other fields like version. So whenever Kubernetes changes this object, I will receive a notification with watch, and when I do next pull of all the objects, I will get an object that identifier has been changed. So I'm just doing diff between two hash sets, and I automatically know which are the old objects, which are the new objects, and which are the modified objects. So what happens that on every cycle of this snapshotting and diffing, I basically categorize them into the added, updated, removed, and I go and ask Memgraph to either remove, add, or basically update. Yeah. But one thing though, for example, like objects like containers that are not first class objects of Kubernetes, there's no easy way to track them properly to keep updating. So what I do, these logical objects are completely removed and added back. But again, you don't get them in this huge volume to be removed and added, which kind of makes my life a bit easier. Matteo, I hope that answered your question.
Let's see if yeah, he don't. I mean, I guess he did. But yeah, Mathieu, if you have kind of a follow up, then I would maybe suggest just reaching out to Art kind of directly as we go.
And I think with Drift is like, you know what, like, I mean, we want to be as much perfect as possible, but once in a while you can actually recompute the whole state. And this is one of the flags I have. Like once in n minutes, you say, you know what, I don't want to, drift too far. Let me recreate the state and then start this loop again. Okay,
Uh,
let's move to
Matthias
the
says,
second.
thank you.
Yeah.
Yeah, Matthias says, thank you. So
Okay,
that's good.
cool.
And then Ante had a separate question, which was the top one.
Sure. Have you think about the different use cases for this? So obviously the optimization from kubectl 5 commands to a single command is big. Is there anything else that you have think about? And it's a good question. Like modern coding agents and frontier models are really good. So the other day I was like, okay, let me do this experiment. Let me ask a very simple questions. And what happened that of course, I explicitly told, for example, Codex, hey, use always Python to generate code and execute it and give me the result. Yeah. So what happened that, actually in terms of token efficiency, it's more efficient for simple single object pinpointing, right? But once I start asking it, hey, let's do multi-hop, all these examples that I showed in the demo, then the the solution with Memgraph and MCP, it's actually twice cheaper in terms of tokens. So because, but it also solves another problem for the model. It has to write a Python script that runs 5 different resources. It has to join them properly, and you have to make sure that it, I mean, you cannot make sure, but if it made a mistake in the joins, you will not know it, right? So where else it can use, I feel like because reasoning models are really good to understand what you want if you define well. Plus, on top of that, you have a schema. I think this tool can be applied in many things. For example, let me think quickly. Okay, I know how it can be used to detect problems that have happened, right? You see, for example, you see the changes in the cluster, you can have a trigger. Oh, like someone updated the component from level A, from, for example, image A to image B, right? And then you see the spike of the alerts. So if you make this system bigger, not only know about this the clarity way of the graph, right? That how they're connected, but you also give eyes like metrics and logs. You can combine all these things to kind of try to create an automatic SRE agent that helps you to investigate the problems. Of course, that becomes even bigger problems because, okay, how you make sure that it queries the things correctly in terms of PromQL, like logs, how they're, like what is the format, how do you make sure that actually whatever you're querying in that component that you updated. So, I mean, there are a lot of challenges there to do as well. But generally speaking, whatever you can represent as a graph, then you can make a LLM to help you out to query that graph.
Cool. Final question it's in the chat this time. So Akshat asks, can you explain a bit more on the snapshotting and incremental updates? Did you follow some default name conventions for node labels and relationship types, basically, or did you come up with what LLM can understand easily?
Sure. Let me. I think if I share my screen, that would be the easiest way. So this is the very original prompt. Of course, with coding agent, it doesn't work like that way. What coding agent does, okay, let me explain this part. So these are the rules that Cypher query, how it has to be generated. And then, sorry. Yeah, sorry, and then I say, hey, you must consult this reference. Yeah, this is a single source of truth. And then I'm saying these are all the nodes that exist in the cluster. This is basically object types in the graph database, and with all the properties defined. Yeah, and then I tell the model that these are the connectivities. For example, the container is a part of a cluster. The container runs on a pod. So this information is provided for the evals. This information provided as a prompt, so then the model can can understand what it's actually going to do. So this is part of the second question about the naming convention. So I actually followed what Kubernetes is doing. That's kind of the beauty of this problem, because I hoped that LLM during the training, it has seen so much of all of this. This is actually full package name plus the type name in the Golang or whatever that is used to define, for example, the deployment spec. So, and my idea was like, if I add, like knowing that LLM has all of this knowledge, plus if I defined the full specification of the types that I used, then LLM will be able to kind of navigate this complexity. So basically, the naming convention, I just followed what is in the Kubernetes space, and I added my logical types just to make sure, for example, that I can model something like pod, something like container runs on the pod. Because if you just take plain Kubernetes, there is no simple way to define it without looking to the pod spec and the containers running the pod spec. So it's not a graph representation anymore, right? So I hope that explained I hope that explanation answered the question. Okay, can you explain a bit more on the snapshotting and incremental updates? Okay, let me stop sharing my screen. Sure. So look, there's a Kubernetes cluster, right? There are like all these objects running there. The way we access it using Kubernetes API. So, okay, but the thing we know that Kubernetes does not change dramatically. Of course, I mean, if you just say, hey, kill the node, kill all the pods, etc., it will change dramatically. But most of the time, in a steady state, there are like a couple of events added, maybe a couple of events removed because of eviction. Maybe a pod get provision, maybe a node get provision, maybe a pod is added, maybe something is reshuffled. But the idea is like, the first time you just launch the app, it doesn't know anything about the state. It goes and takes the whole state of the Kubernetes, right? It goes and says, give me all the nodes, give me all the pods, give me all the events, give me all the services, basically all the 27 types of objects that can be represented in the Kubernetes. It pulls all of them. Okay, now it has this initial state. So, and then Kubernetes has a cool concept to not overload Kubernetes API. You can actually subscribe to the changes of specific resource types. So instead of going and always every 2 seconds reading everything again and again, I use different thing, which is I'm subscribing to the changes of all these resources. And when the change happens, Kubernetes sends me a notification about the changed objects, and that changed object is pulled back so I can see actually what the object that is changed. So this way, you basically have a very slow, I mean, you can of course fire all of these things in parallel, but Kubernetes API might not be happy, but basically quite slow initialization. But the steady state, when you're diffing, you basically quickly get what has changed, and you propagate all this. Basically, the one thing important, so I have in-memory representation of current state. Yeah, it's always in my memory, so it's very cheap for me to update it. It's not even in Memgraph. I keep it in my memory, in the memory of the Rust application, MCP server. So, and every time when the changes happen, I automatically basically, because the hash map, I can just update everything and remove everything what is possible. And that's it. And then I have a previous state of the cluster, current state of the cluster, and I do a diff between them. Again, diffing is very fast because I have identifier, I have IDs of the object that is specially hashed in the way that I actually know when I take previous state of that object and current state, I know whether it's the same or not. And if it's not the same, then I decide whether it's updated, removed, or added. Hope that also answers the question.
Yeah, there's a thumbs up. There's a thumbs up on the question, so that means job well done. Amazing. So we're at time. So literally on the hour. Thank you everyone for joining, and especially thank you Art for sharing all the work that you have done. I am sure that obviously kind of it was informative and very helpful to people managing various Kubernetes clusters, and there's probably a lot more to come. So as a follow-up, we'll share obviously kind of the GitHub repo, and people will know kind of about you, as so hopefully they kind of respond and reach out if they have kind of any questions as well. So yeah, thank you so much once again, and yeah, we will be in touch for the next one.
All right. Thank you.
Have a good
Bye bye.
one. Bye bye bye.